Okay, so yeah, this part, I think this is even more relatable, easier to describe, motivate than the auction. Like auction was like obviously a very significant, am I? Yeah, okay, right. So congestion and traffic routing, and why are we talking about this in a workshop about spins, games and networks, right? Okay. So game theory, we didn't talk a lot about game theory at all. I mean, it was just there in the in the background. So game theory is just a sort of a mathematical subject study of agents, rational agents, and the competition and cooperation between them. So the rational agents, because they want to maximize their utility, payoff, welfare, whatever, right? They are just sort of thinking about themselves and the interaction that results in it, the way they would think about it, that they would act, and so on and so forth, right? So in that auction scenario, we saw how people would reason about what they should do versus what others are doing, and so on. So auction is obviously a fabricated, contrived setting or a marketplace where people it's something that we create where items can be exchanged among buyers and sellers. But there are other games that we can see which are more natural, and nobody is really sort of fabricating or creating them, but they are games nevertheless. So traffic is one such example. So what we call it, at least I like to call it, is games in the wild, right? So this is an example of a Bangalore. Sir is from Bangalore. It just reminded me, like nowadays whenever I search, I search for traffic, congested road, an article pops out talking about how worse Bangalore traffic has gotten, right? So this is this seems to be a thing. So this is some flyover in Bangalore, and you can see it's sort of layered. There is traffic here, and so on and so forth. Now I like this picture in a way because there is there is a divider here. Oh, okay. So there is a version of this where basically this divider disappears and the traffic sort of, it becomes one lane. So you can imagine in India nobody maintains their lane. People are constantly trying to overtake, and you can imagine the mess it creates. This looks bad enough. I can't imagine what happens when it becomes like a single lane traffic. Okay. So what are the people here trying to do is my question. What do you think? They all are trying to get to wherever they have and as little time as possible, right? But the present, so I am trying to do the same, you are trying to do the same, we all are. It's just that the presence of people and how many of them sort of affects how I experience my travel time. That's what it is happening, correct? Okay. So everybody is being selfish in trying to get to use the shortest route from point A to point B, and doing so is sort of creating this interaction between various agents, in this case traffic, on a road network. So can you tell me, if I talk about congestion game, I basically said it, it's something that we experience every day. I mean, I do it every day. So this is basically literally a map of, this is where I live, this is where IMSC is, okay, and over here is this place, there is this Sholinganallur crossing, okay, and over here is this place called CMI, Chennai Mathematical Institute. So during this semester, I was teaching a course in algorithmic game theory, and one of the classes, there were 2 classes per week, one of the classes I used to teach in CMI, okay. So every morning, the decision I had to make was, so this is the map I showed from my house to this place. There is another map that I oftentimes show, I mean at least I showed it to those kids to explain what this sort of thing is, which is basically there is a route to go to CMI from my home which goes via Kovalam and then comes back up. The other route is to go via Sholinganallur, the sort of experience OMR traffic, especially now that construction is going on for this metro and so on, okay. So there are times, by the way, the distance from this side to this side, and after teaching the course I actually come back up to IMSC. That's what I used to do, okay. The point is, this is the straight route and this is the shortest route per distance traveled. Sometimes based on the time of the day, and from my home, from here to this place in CMI, the distance via this Sholinganallur and via Kovalam is just about the same, maybe a few, fraction of a mile, okay. But there were times in the day when the amount of time the Google would show, the Google map would show that it will take 30 extra minutes if I take this Sholinganallur crossing versus the Kovalam route, okay. So, this tells you there is a difference. This example is often shown as sort of a very canonical example in explaining how does game theory differ from optimization. Everybody understand this topic of optimization? Here are some constraints. You want to find a solution that satisfies these constraints and you want to maximize or minimize some function. That is what optimization is, right. Now, over here there is a notion of optimization here as well. Travel time, I want to minimize my travel time. So, what is actually different between if I told you there is a difference between classical optimization theory and game theory, what is it?
Are you optimizing based on the decision? Your decisions
Decisions what? In optimization also there is this notion like, do you take this path? So, let us think of this as an optimization question here would be shortest time, right. So, I look at a map, the decision is which route to take. I mean, there is also a route via Sholing, I do not know why anybody would actually cross over to Sholinganallur to come here. Again, almost same distance, but insane, okay. Like this is much straight, this still experiences traffic, but not nearly as much. At some point, I have to cross over from ECR to OMR, that is the point. So, the question is where. So, a normal optimization question would be look at a map, find out which path you should take based on time, based on distance, right. Game theory says the time travel is not a static quantity that can be just read off the map at all times of the day remaining the same. Presence of traffic, presence of other people on the road at the time of my travel is what generates the time of is what decides my time of travel. So, the shortest path question, which is a classic graph theory question, right, distance between vertices, where the links between vertices have some distance, some positive number associated with it. It is a classical graph theory question. The game theory question, the analogous game theory question would be shortest time of travel, right. Clear? Okay. So, this is what a congestion game basically captures. You have entities, in this case entities can be people or cars, whatever, it is the cars that are sort of creating the traffic. So, let us call it cars, whose behavior is not entirely predictable. When I start out on the day, do I know what other people are going to do, how many people are going to leave the road, are going to use the road at the same time, nothing, right. I have just some estimation based on historical fact, like I travel every day, I have been doing so for many years. So, I generally know how much traffic I will experience at that time of the day. But that also changes based on other things, maybe it is a holiday, maybe it is raining and so on and so forth, right. But most important thing is I have no control over what others are doing. My only thing I control is whether I am going to travel this route or that route or travel at all, correct? Okay. So, that is basically the action space of each individual. So, I am one agent, every other person is thinking the same way. So, our action is whether to go out and which route to take, which path to take, right. But what time of travel, what time, how much congestion there is, this, even though I made the decision entirely on my own, not having complete information of other people, my experience is affected by what others are doing, okay. So, this is what game theory tries to capture. This is the other thing. If I had better information about how many people are on the road at this particular point in the day, then that might change my decision. This is basically what these sort of traffic, real-time traffic updates and so on and so forth try to do. Previously, decades ago, maybe this is well before you were born or whatever came into census, people had no such information, right? That there was no, you could not just switch on a smartphone, look at the map, see how much traffic is, blah, blah, blah. People just use their everyday knowledge and just sort of guess estimate, let's say. Okay. So, this sort of thing, when I can change my behavior based on what others are doing, is what is called strategic behavior. So, if you go back to the auction setting, the strategic behavior over there was what? Overbidding, underbidding and so on and so forth. The rules of the game were they had to submit a bid. There was nothing more they could do. So, you have to stay within the parameters of the game. Here, traveling or not to travel and which path to take. But within the rules of this game, there are decisions you can make. Over there, it was a choice to overbid or underbid or tell the truth. Over here, it's a decision as to which path to commit to, which route to commit to. Okay? Okay. So, essentially, when the outcome of one person, payoff, utility, whatever, depends on the actions of other people, that's what is called a game. And congestion game is a type of game where what we have are these vertices or nodes and sort of communication. It could be communication line, it could be transportation line, like cars and buses or communication network and so on. So, there are these links between these vertices and you have a load or a cost function, not load, cost function or latency function associated with those links. That tells you that if this much amount of traffic were to pass through this link, this is the amount of delay that people would experience, that the things that are passing will experience. Okay? That's the setting for a congestion game. Any questions? Okay, we'll see some examples and then maybe this will be clearer. Okay. In 1920, so you can understand transportation network have been around for what, millennia in some form or another. People have been trying to transport goods, people and so on forever. This sort of traffic congestion thing, while it's a particularly onerous problem for our modern days where so many people go to work and have to travel long distance, but the mathematical problem has been around and people have tried to study it for a long time, in particularly operation research people, engineers and so on. Lot of the time when they decide to build roads and train networks and so on is based on these sorts of studies, that they want to provide faster connectivity, they want to provide connectivity to intermediate space distances, but those distances are not economically viable, so they want to connect it to bigger stations and so on and so forth. Okay? So, in 1920, this gentleman by the name of Pigot studied this highly oversimplified network. Okay? So, you have a source A and B, this is one road and this is the bottom one. Okay? There are two paths to travel from A to B. The difference is, if you travel via this top link, the load you experience is linear, the latency you experience is linear. So, if you send X unit of flow, the amount every unit will experience X unit. So, total travel time experienced by everybody would be X square. Okay? That is how to interpret. On the other hand, this link experiences a latency of constant value. Okay? No matter how many people are on the road, they will all experience the same amount of time. So, the total time would be, if X units are flowing through, it will be X times 1, which is X. Okay? This is how we interpret this.
Exactly
cost, latency, cost. So, now let us think about, suppose there is one volume of traffic, like the background, let us think whatever volume of traffic starts from A, they all want to get to B, and the point is how to sort of split the traffic. You understand, like if all one unit of flow goes through this, how much would be the latency, how much would be the delay, how much would be the travel time? One, right, it will be 1. If everybody travels through this, what will be the delay? Again 1. So, as long as everybody is going this or this, it's basically the same thing, correct? Now, I as an individual have no control over what others are doing. Which path should I commit to? Is there a path that I can commit to, knowing that no matter what others are doing, this is at least as good as doing the other thing?
Second,
This one? Why?
because it's independent of if others are choosing that, shall always.
That is correct. But suppose I take this path, okay? Others are taking this path. Do I not experience a lesser time on this?
But the best possible time in the other path is equal to the.
Correct. In the worst case, rather, if everybody were to travel through this, they would experience the same time that they would travel if they were to travel through this. But if fewer people than the entire volume took this path, all those people who are on this path would actually experience strictly less time of travel. No worse than this, but perhaps strictly better. Therefore, as an individual, it makes sense for me to commit to this path. In the worst case, it will be exactly the same as this and this, but maybe I will actually experience a shorter time if even a small non-zero fraction moves to this path. Is it clear? Think for a moment. Do you see? As an individual, I have no control of what others are doing. If everybody went through this, I know it's the same time travel. But if fewer people did not take this but took this, I would experience lesser time of travel.
Also, X can be anything.
X is the volume of traffic. So, you have one unit. Think about X as fraction. Half, 1/4, 1/3, that sort of thing. Okay? Yeah. Right? Okay, let's see an example. So, okay, I actually had this picture. So, everybody going through this, the time of travel would be 1 times 1, X is this, X is basically 1, the whole volume unit, right? Now, in this example, the same picture, let's see somebody controls the traffic or something, whatever, doesn't matter. People just came to this decision that I'm going to fork. So, suppose I send half unit through this and half unit through this. Now, can you tell me what would be the time of travel for people on the first link versus the people on the bottom link? How much is first link? Half times half, 1/4. So, each you are, right? Each individual is basically experiencing this much. Together, there will be half times half, right? 1/4. This one is actually half because it's each individual is experiencing 1 unit of time delay. So, half times 1 times 1. Okay? This, I would tell you, even though it looks very different from that auction type of thing, but it's the same kind of thinking that I have no information what the others are doing. In the second price auction, truth telling, stating my bid truthfully is my dominant strategy. No matter what others are doing, this is the safest strategy. Same thing is the thing here. Yes.
When you say half times half, like that's the total sort of
yes,
cost.
total times half. So, all of us together are taking this thing. Now, if you, yes, so what was your question?
Is trying to minimize their own cost. So,
Okay.
what's the point of looking at the total cost? I would still say it's half in that total half.
Yeah, but then if you take the ratio, you would still have that is better than the other, right? So, it's like it's the volume of flow. Total, if this total is less for something, if you divide it, you'll get still this is half and half, right? So, the same number of units of people are moving through this and through this, but the numerator here is smaller than the numerator here. So, total individually also, okay, fine. Maybe if you want to think individually, I experience a strictly better improvement here and there, right? Now, the point is it clear what his question was? I framed this thing in terms of total time of travel. He said, I don't really care about total time, I am interested in mine. But then the point is, if all of us together experience this much of time, I can divide by the number of us who are on this track, right? And I get an average time of travel. Here I have split the traffic half and half. So it's like total time traveled by this top arc is strictly less than the time of travel by this, and I divide both these things by the same quantity half. So basically I still see that individuals on this path are still doing better than individuals on this path. Okay. Obviously, this kind of calculation would differ if I put different amount of load on the top and the bottom. Do you see? Is there any other way to split this traffic so that people on the top, so this is the calculation, right? Time of travel and take the this thing and so on. Convince yourself that splitting half and half is actually the best outcome. So if somebody were trying to do traffic control, and oftentimes this is what happens, they would try to route half the volume of traffic through this first and the half through this. Okay? But in the absence of that, everybody is going to try to think, oh, taking this will give me no worse outcome than taking this. Therefore, I should take this. Okay? So now, this was the time of travel when people thought selfishly. This is the time of travel when this sort of splitting happened, a balance splitting. Do you see the difference? The ratio, the difference here I means ratio is 4/3. Right? Okay. So, can you tell me what is the price that selfish behavior or selfish behavior in the sense that unilateral thinking just about oneself actually cost? It is quantified by this amount. It could have been this, but it is this, therefore the ratio is 4/3. Okay? We will revisit this concept a little later. So, tell me, from society or just community's perspective, it's easy to see that this is the better scenario, right? Everybody experiences a lesser time of travel.
But like, I mean, in the first, if everyone takes the upper part, then we are taking 1 unit of time.
Yes.
So in the second one, the people going by the bottom part are taking 1 unit.
So they are taking 1 unit, but how many people are going half?
Those
1 times half. That's what this quantity is.
Yeah, so for those half people, there's no difference. So they don't see a difference. So
Yes, but their difference is half versus this.
but
This is 1 divided by 1 is still 1.
yeah, but the person, like, you're thinking about yourself, right?
No, this is why I am saying this is not the dominant strategy. If you are thinking only about yourself, this is the natural thing to commit to. I am saying, but this is the optimal outcome.
But that is, the right one is better for some people, not better for all the people.
So, optimal outcome does not necessarily mean it has to be beneficial for everybody. That's why I am saying, from the community's perspective, from everybody's standpoint, it makes sense to split the traffic. These are the people who are experiencing higher time of travel than this, but together, the improvement is 3/4 versus 1. This is the sort of thing that happens when you want to optimize over an entire group of people. Some people still will experience a lesser payoff or lesser utility than other people, but together it's beneficial. So tell me, do you see that this sort of thing, so here over there in the auction scenario, we didn't actually have this idea of what would be the social optimum. All we had was these individual guarantees of non-negative utility, maximizing welfare, and so on and so forth. Right? Here, the things that we are talking about, that what we would want to is to improve everybody, like the travel time for everybody taken together who are traveling the road network at this time of the day. We are not interested in improving the sort of utility of one single individual or a small fraction of them. Yes.
I think it is useful to say that maybe the traffic control randomly gives half of the people in group A, group B.
So yeah, that is the point. Traffic control, they don't choose and select you to penalize you, right? They just divert half volume, some amount of traffic on this route and that route. That's exactly the thing. Why this is the optimum? That's the simple math. If you put a different amount of weight on each of this, you will not get this sort of optimum time of travel. Splitting half and half is exactly the best possible outcome. And what the advantage here is, the ideal outcome would be, because of the problem we are discussing, travel time, people traveling together on traffic, the goal here is different. It's not about maximizing individuals' travel time, but everybody is together. This is called sort of minimizing congestion on the road or congestion on networks. Okay. All right. So, the question is, in this particular scenario, in different scenarios there can be different objectives, but for this kind of a thing, the objective, one of the desirable objective is to minimize average travel time. So, the question is, how far, looking at Pigo's example, how far can we veer from this objective? That is the ideal outcome, minimizing total sort of average travel time, versus how poorly can we do in terms of that objective. That 4/3 quantity basically quantified that. If everybody thought selfishly just for themselves, they would opt for the dominant strategy, and the travel time sort of booms up, but there is a much better outcome, that would be 4/3, 3/4. This thing, this sort of comparison is what is called price of anarchy. It's, in this example, when stated, it means it's the travel time in this dominant strategy equilibrium. Dominant strategy equilibrium just means a situation where everybody is sort of selfishly just thinking for themselves, versus the minimum possible travel time. When the game changes, the notion of price of anarchy also changes, but essentially what it tries to capture is, what is the worst possible equilibrium behavior versus the best possible equilibrium behavior. Okay. Yes. Okay. Now let me ask you, here look at this, I have changed the cost from x to x to the power p. P is some large constant. So, it is a polynomial time latency function. Can you tell me what should be the dominant strategy here now? It is still this thing, right? Because I am still assuming 1 unit of volume of flow. So, again, even if everybody takes this thing, this would be, x would be 1, 1 to the power p is p, and total time taken would be 1. The same thing if even one person travels through this. So, again, this is still the dominant strategy. But can you tell me what is the minimum possible travel time that traffic control can actually attain? It is a bit of math. So, you can see, suppose it is a thought experiment, suppose all unit is flowing this, I divert epsilon unit through the bottom arc. Okay. So, that is what this is, 1 becomes 1 minus epsilon, the rest of the traffic goes through this. If you do this, and epsilon is very small, okay. If you do the calculation here, the travel time will basically just be this. So, epsilon times 1, because this is the latency cost function here, 1 minus epsilon to the power p times 1 minus epsilon because of this quantity and so on. So, this is what you get. Now, can you tell me what is the optimum sort of traffic routing scheme here? Think as P being very large, like this is a very high cost edge. You can examine this. If P is very large, what happens? This term falls away, right? So, this entire term tends to epsilon, correct? So, when P is very large, epsilon being very small basically means travel time is basically becoming arbitrarily close to 0. So, you see how large a difference there can be. This is basically, it's obviously a thought, like you can never have zero travel time, but this is a mathematical way of thinking that over here you experience the maximum possible travel time, but here if the cost function is very high, meaning the P is very high, you can actually, by routing little bit of traffic, keeping most of it on the top part and little bit down here, you can actually experience a significant improvement in time. Okay? So, this sort of network has very high price of anarchy. Okay? 1 versus 0, over there it was 1 versus 3/4. The difference is very, very large. Okay. So, this is basically, because this is 0, it is basically unbounded, it means absolute mayhem. Okay? All right. Now, you know this, that sometimes in order to mitigate traffic when there are a lot of complaints and so on and so forth, they build road networks, right? They build additional bridges, roads and connections and so on and so forth. It happens all the time, it is part of city planning. Do you think it is, does it always alleviate the problem? You are nodding your head, like give me a very concrete example in which they built roads and the situation became worse.
Showed a half-built bridge.
Oh, that is very drastic. Let's say the bridges are built, the roads are functioning, then somehow still it has a sort of counterproductive effect on the people's experience.
Metro construction.
Oh, but the metro construction is a temporary thing, like once the construction is over, right? This is, so yes, those are things, but those are not the gates. Literally over here, we built a road, the road is functioning, everybody is moving, and now the traffic situation is worse. That sort of thing.
They can be more cars because of
More cars because of more roads. Okay, let's say the car supply, that actually happens, I think that's what happens in Delhi. Each time they finish a road, that highway project, then more people have bought more cars. Okay, I think that's just a standard joke. In Delhi, people started with 1 car, now they have 3 cars, like by the end of the construction. Suppose the supply of cars was also the same. Can that happen? That now still situation is worse, yes?
How people choose to act given that road.
Right. And where can it go crazy? Basically that, right? Like ultimately people's travel time depends on how others are doing it. That's basically the essence of these sorts of analysis.
directionality.
Directionality meaning?
Like if a singular road can accommodate two-way traffic, but there is no distinct separation between the two.
Okay, those are practical, this thing, sure. Suppose this was a one-way road. Then, sure, those are absolutely realistic scenario. Now, somebody said about this construction project that creates so much problem for so many years, right? That's actually true. What they do is a cost-benefit analysis. They say, okay, this is just a temporary. Even if it's going to take 5 to 10 years, still generations of people from this onwards will enjoy better traffic. That's the sort of thing that they think about. Okay, so here let's look at this. Okay, this is just slightly more stretched out Pico version. So from okay, I somehow changed this. So this is origin and destination. So from here you go to V, and see these direction basically mean this is the only way the traffic can flow. There is no both sided. Okay, so here you have the same thing, linear cost, latency function. Here this is this uniform constant cost. Here the situation is opposite. Over here people this is the unit. This is the linear. Okay. Here tell me quickly what would be the dominant strategy. Is there a dominant strategy? Can I reasonably think about this traffic, this network the way I did about Pigo? Yes, they are actually similar. And that's part of the difficulty. I cannot say that no matter what others are doing, taking this route is the same, is at least as good as taking this route. Part of it is because here, over here if I pay this sort of a linear kind of a thing, but later on I am going to experience that constant staggered traffic weight sort of thing, right? Similarly here. So in this kind of scenario, I can't say that this route is at least as good as the other one. This is the situation where a dominant strategy actually does not exist. It really depends on what others are doing. So there is no way of sort of thinking about this network the way we did of Spigo. In this case, somebody really has to, like, people can basically commit to anything, do anything without any guarantee of what would happen, right? Best outcome, however, is still to balance traffic like this. This is a mathematical abstraction. This would be the ideal outcome. Whether or not, it's highly unlikely that the people would be able to self-regulate like this, right? Okay. So now travel time, same type of calculation. This twice is because it's splitting across this and so on, right? 3/2. Now, city planners build this super highway where you are telekinetically basically traveling from V to W. So, latency cost is 0, means in 0 amount of travel time you can go from V to W. Okay. Now, is there a dominant strategy? What? Yes. Now it makes sense for everybody to take this thing, and therefore everybody will commit to this path, 0 to V to W to D, right? And then what is the travel time experienced by everybody now? You can do this calculation, it's actually 2, right? So this was exhibited by Braze in 1965 and is known as Braze paradox. This sort of phenomena, when we over provision, we provide a sort of a facility which is supposed to bring down cost, but actually essentially has an opposite effect, because you have this sort of a non-cooperative selfish behavior of the agents, is often named Braze paradox, even if the setting is not necessarily, let us say, congestion games, okay, because of this sort of phenomena. So, was it clear, right, that sometimes building these sorts of things, and I honestly think this sort of thing is actually empirical, it is a lived truth for many people, because now you have this shorter distance, everybody thinks that this is the best thing to take, and that is where the clogging up of this thing takes up. And that road that I was saying, whenever I go from ECR to OMR, and I somehow have go a lot on OMR because, I mean, hospitals and other things, my parents, constantly we need to go there. So, sometimes, you know, taking these side alleyways which are very tiny, there is a chance that if somebody is coming from the other side, you will really get blocked. It is well worth the risk, in part because you can just completely, you know, circumnavigate the big congestions that are brought on by the metro construction, right. So, I am just saying, like, these are some of the ways we think about these things. This is our response to a situation which is for which we know, like, in a congestion type network. Okay. So, here what is it? So, you see this is 2, this is 3/2. What is the price of anarchy here? Again 4/3. So, that was Pigo, this is Braze. Both of them are showing us price of anarchy to be 4/3 when the costs are linear. That Braze had a unbounded price of anarchy when the cost was not linear, right, when it was high polynomial, had a high degree P. But these are linear costs, right. When the cost functions are linear, then we see 4/3 is the price of anarchy that emerges from here in both situations. Do you think this is like a coincidence, or there is some general phenomena taking place? Okay, keep that in mind. So, in Pigo network, we saw that the loss due to, okay, the 33% is just that 4/3, like 1 minus 4/3 quantity, 1/3, right. Turns out, okay, let us pause for a moment and ask, Pigo and Braze are very simple networks, very, very simple. What if we had a more complicated network? Can we imagine a worse scenario? Right? Over there, the Pigo network, very simple, but the latency function was a polynomial. There we saw very high price of anarchy. So, now I am saying, let us say the cost function remains linear, but the network is very complicated. Can we have higher price of anarchy? Can you imagine? Can you tell me something?
Would there some traffic and some Varanasi which takes 1 or 2 hours to get rid of?
Yeah.
Just one intersection.
Correct.
So there is a lot of price of energy.
Correct.
It's not linear function, but it is
Yes.
also-
That is this. That is the what I was trying to say. That this latency function, right? Who is telling us what this latency function is? It's basically again, there are researchers who actually study traffic pattern, and they will study traffic, road transportation, shipping. Shipping lanes, you know, highly high revenue sort of industry like shipping, you know, global shipping and so on. Huge amount of traffic. There are certain a few years ago there was this whole fiasco in the Suez Canal. Do you remember? Like one container ship sunk or like offloaded his stuff, and so many ships were held up. Like it led to global supply chain issues on things that, I mean, one wouldn't even think of, like really my stuff is stuck in Suez Canal, that sort of a thing, right? Okay. So yeah, that's the sort of thing that you're saying. Like those are not necessarily linear, but I'm saying just even if I have a linear simple enough cost function, but a very complex network, can I anticipate worse price of anarchy? So, I mean by complex network I mean many more vertices, many more arcs and so on so forth and so on, edges and so on. These are sort of generally captured as graphs, or you can call them networks and so on. It turns out when it comes to, if the cost functions are nonlinear, we know it can, right? It turns out when the cost functions are linear, no matter what network you have, price of anarchy cannot be worse than 4/3. It can be actually shown rigorously using math. And here I pause and say a few things about theoretical computer science. You are here in a research institute which does theoretical research. I work in theoretical computer science. We always want to encourage people to look at theoretical computer science as a topic of higher studies. It's not a subject that any of us study in high school. It's a weird thing. All of us know about physics, chemistry, math, biology. During our school years, we are not taught about theoretical computer science, but this is a domain which sort of sits in the juxtaposition of math, computer science, and now all these other things like economics and sort of robotics and so on and so forth. Like anything, whenever you want to study sort of faster computation of something, whatever the thing is, that's the domain of theoretical computer science. Now, in 1920, Pigot identified a network where you can have 4/3 price of anarchy or unbounded price of anarchy. About 40 years later, Braze discovered or exhibited this paradox where you can have really bad situation and the price of anarchy remains 4/3. In all this, it was not until 2002 somebody actually asked and answered this question, how much worse can it be? How much worse? What's the worst case price of anarchy you can have for a given class of functions? This paper studies that. For linear or affine rather, it's shown 4/3, but they give a whole list of if this is the class of cost functions, you get this much value for this and this, and each one is actually tight. Okay. So, this sort of thinking of worst case behavior and so on is the unique domain of theoretical computer science. So, the problems were sort of the domain was known, but nobody asked to think how bad can it be. Okay. So, look, let me just, I don't think I have the list of, I need charge. I don't have, Shiva, do you have a charger for this? I think my computer will sort of, I have it in my office. Let's go quickly through this. So, we'll come back and then chat about this a little bit more, but let's move on to, so this is sort of the thing what we call selfish routing. Yes. You will edit out this fluff, right?
Yeah.
Okay, it's in my bag, green bag. charger and this thing cord. So selfish routing. The type of routing that we saw is that of non-atomic selfish routing, where basically you have volume of traffic, but each individual has very small contribution to the overall traffic, like one car, one truck and so on in a road network. Okay. Can you imagine the other scenario where there might be fewer people, but each individual asserts a significant sort of footprint onto the traffic network, and that's what we called atomic selfish routing. Okay, yeah, road traffic, private users of a communication network. Like I'm an end user, I use internet, sort of broadband. There are other people, if all of us log in together, there's some congestion, blah, 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 right? Certain times of the day, especially I think it happened during COVID, everybody's trying to work and they were slower, but now things have gotten much better. So can you think of the other case? That's what it's called, atomic selfish routing. And can you give me an example? Shipping lanes? Okay, actually that's not a bad example, yes. So shipping lanes are a very good, it's a good example. Shipping lanes are something that only commercial ships sort of go. So it's not like people are not taking their yacht and going on a, utilizing shipping lanes. You're right, some shipping companies are huge, they are sending a lot of traffic, good. Anything else?
Data centers that control like edge connections basically.
Correct, that's good. That is also an example. They do control, each control a huge volume of traffic passing through those lanes. Another one would be these sort of internet service providers, right? They are also participating in the network and they are actually routing traffic, right? So, okay. So, there are analytical studies studying non-atomic selfish routing and atomic selfish routing, and we study their worst case behavior and so on and so forth. So, yes, I think it's, yes, good, thank you. So, I won't present any sort of theoretical this thing, but let's move on to, okay, I am doing this thing. So, let's talk about some cool facts about congestion games, okay. Why they are, firstly, they are obviously very important, we know this, but mathematically also from the analytical standpoint, they have some very special properties that other kinds of games don't have. So, this type of study of congestion games was initiated by this gentleman called Robert W. Rosenthal in 1973, and he showed some of the sort of the fundamental results in this. He basically mathematically framed this. In particular, he said that if this is a congestion game is a game, like we saw in the very first slide, do you know the meaning of Nash equilibria? Somebody please tell me what is Nash equilibria? You want to tell me? Yes.
It's a set of strategy of players where if any one of them diverge, then it cannot get worse off.
Strictly better outcome.
Yeah.
Whatever outcome means, in this case it means improved travel time. But the main point, that's actually correct, the main thing to focus on is one single player unilaterally deviates. That's what's called unilateral deviation. Everybody else remains the same. So it's like we're all going on a wherever from point A to point B. Only I decide to take a different route. When this sort of a deviation does not give me a strictly better time, travel time, okay, then we say that is a Nash equilibria. Okay. Now, this sort of thing where I choose one other action to play, it's called pure strategy Nash equilibria. Do you know what is a mixed strategy Nash equilibria? Somebody? Okay. So, let me try to give a sort of a mental picture of what a mixed strategy Nash equilibria is, okay. So, mixed strategy Nash equilibria is like, it's a mathematical abstraction where individuals, let's think about strategies, mixed strategy in itself. If I say this is exactly the route I will take, A to B using path 1, he says I will take path 2 from A to B. These are like deterministic choices versus probabilistic or randomized choices, where these are the possibilities. There are path 1, path 2, path 3, all connecting point A to point B. I choose path 1 with some probability, some path 2 with some other probability, and path 3 with some other probability. Only requirement is that these probability masses should add up to 1. Okay? This type of thinking, this kind of a behavior is what one would call mixed strategy. I am mixing over my possibilities and I am adding some weight. A pure strategy in Nash equilibria is when I choose a path and put probability weight 1. So, a mixed strategy is a generalization of a pure strategy. So, we define mixed strategy in Nash equilibria in an analogous way. Main point is to say that a set of mixed strategies for individuals is a mixed strategy in Nash equilibria if nobody has a deviating strategy, no individual has a deviating strategy. That deviating strategy is, let us say, an action, a pure strategy itself, such that this person gets a strictly higher expected payoff than before. Okay? Because we are using probabilistic argument, instead of precise payoff, we talk about expected payoff. Okay? Now, landmark result in the theory of games was by this gentleman called John Nash. You may have heard about him. There is a wonderful book written on him, Beautiful Mind. A movie was made. People won Oscars for this. Okay? So, he put forward this idea of Nash equilibria and showed that every finite game, meaning a game that has finite number of players and finite number of actions available to it, that is a finite game, always has at least one mixed strategy Nash equilibria. Okay? So, this is a we believe this is a good outcome to have, because it means that nobody is trying to unilaterally deviate and move to some other outcome. It is like a steady state. Equilibrium in this case means it is a steady state. People understand that just unilaterally changing, deviating will not give them a strictly better payoff. Turns out very simple games do not necessarily have a pure strategy Nash equilibria. They would have a mixed strategy Nash equilibria, but not necessarily a pure strategy Nash equilibria. Do you know, can you think of a simple game like kids game which does not have a pure strategy Nash equilibria? Rock, paper, scissors, exactly. Okay? Because no matter what you do, you play rock, I can play scissor. I play paper, you can play something else. No matter what anybody chooses, somebody else the other person can choose something else, that negates this, right? This is why there is no pure strategy. Now, congestion games are a type of games where a pure strategy Nash equilibria always exists. Okay? So, while mixed strategy Nash equilibria are more general concepts, so on and so forth, because of the probabilistic, the randomization involved and all, they tend to be counterintuitive for people to think and analyze and so on and so forth. So, having a pure strategy Nash equilibria is a rare but a very valuable sort of phenomena. So, Rosenthal showed that every congestion game has a pure strategy Nash equilibria. In fact, he showed that the reason this fact may not be as interesting as the manner in which he showed. His proof basically birthed an entire subject of study. He showed this by showing that the behavior of all these players in a congestion game, even though everybody is individually reasoning for themselves, can be captured by a global function which we call a potential function, which exactly maps if a person changes their strategy unilaterally, the change in the potential function captures the change, meaning whether positive or negative, that the person encounters due to the deviation. Okay? So, inadvertently, even though they are not playing cooperatively, they are just thinking for themselves, somehow their action is moving a function which is a globally defined function. So if we understand how to capture that function, the minimum value, the strategy that this function is defined over the strategy space of the players. So the strategy at which this function attains the minimum value captures a Nash equilibrium. Okay. So he showed this direction, that every congestion game has a associated potential function to it, and therefore that congestion game can be thought of as a potential game. Okay. So all the, yes. Okay. Now later on, Moderer and Shapley, the 80s I think, proved the converse, that every exact potential function, forget about the word exact for a moment, potential function is equivalent to some congestion game. You give me a potential function, okay, potential have some sort of specification, I can fabricate a congestion game that has this property. That game's pure strategy Nash equilibria maps to the minimizing value of the potential function. Okay. So now tell me, what do you think these two things taken together allows us to do? Right. It moves the research towards a mathematical question about defining looking at the space of potential functions and understanding their behavior, and basically that allows you a complete control, like understanding of the world of congestion games, which really is a games in the wild. As such, when you look at congestion game, it may seem like, how am I ever going to understand how human beings are going to decide on traffic, like which path to commit to, right? Turns out you don't have to if you know this other mathematical object, which is a potential function. Okay? All right. So now there are lots of types of this thing, potential function. This exact means literally the improvement whenever an agent deviates, the change in the value, okay, of their payoff, plus, minus, whatever, it exactly gets captured by the potential function. Sometimes you can have a more generalized setting where an increase in the payoff of the agent will be witnessed by an increase in the payoff, the lower increase in the payoff, but it's not, the value does not exactly map. This is a much more tighter constraint. Okay. This congestion allows, this framework, if and only if type of thing, allows us to study best response. Like if I'm trying to learn a game, we are playing the game over sequences of steps. I travel every day, right? So it's not just for today that I'm thinking about trying to minimize my time. I'm going to have the same dilemma tomorrow, day after, and so on. So in a way, I'm trying to learn the traffic pattern so that I know what is the best route to take on a daily basis. This is what one would call learning a game while you're playing it. How do agents learn about the game while they're playing it? Is it at all possible? This sort of topic, this kind of questions have become central today due to the ubiquity, or at least the sort of prevalence of machine learning based algorithms, and whatever the promise of AI is for the future. You want algorithm that can learn while doing something. Over here, it turns out to learn this, you basically have to learn the potential function. Okay. All right. So now in recent times, people have used this roadmap to ask, like, are there more general, do potential functions exist for more general kind of congestion games, not necessarily just the one that this study? What is the rate of convergence? Like in how many steps can you show that the potential function will actually converge to that minimum? So there might be multiple paths, some paths might actually loop over them. Is it possible that it loops? Question is, okay, maybe it's not looping, but it's still taking a very long time. What are the fewest number of steps in which a convergence will happen? And finally, what is the computational complexity of calculating these objects? Like how fast can I actually learn about this? Okay, and all associated questions. So I think with that, yes, sure.
Do you have any intuitions to why congestion games have potential functions, whereas in general, for games in general, we can't find those potential functions?
Okay, so the simple answer, okay, so I guess I just said it before. So what happens is, let's think about this road network thing. So, and let's compare and contrast with a game like rock, paper, scissors. So, in rock paper scissors there are no pure strategy Nash equilibrium, right. The road network type situation, the strategy is I committing to this road, you committing to this road, and let us assume we are all travelling from A to B. If there is a better, so you can think about a graph where the vertex set are these strategies. So, from one vertex to another vertex you have a directional arc. If there exists one agent, the difference in these two strategies is just the strategy of one agent, and that agent experiences an improvement in payoff. Okay? So, the starting point is a vertex, whatever our initial this thing, and the sink in this graph is a vertex which has no outgoing edges. By this definition is a Nash equilibrium state. So, what you are trying to find is a directed path from the source vertex, where we are basically just a starting point, to this sink. There can be multiple pure strategy Nash equilibrium, all of them would be sink. So, in this directed graph what we are trying to find is a path to the sink. The moment there is a one-to-one correspondence between pure strategy Nash equilibrium and the sink. This phenomena does not exist in general games. In the sort of a thing, the rock paper scissors, there will be a constant loop. You change to rock, I change to what, scissor, whatever, paper, right, and then we keep on looping. This is why. It is a reachability question on a graph where there will be a path. Okay. Yes.
What do you mean by for more general congestion games?
Okay. So, so you can have congestion game where you have, so I talked about selfish routing and this thing, sorry, I talked about atomic games and non-atomic games. Okay. So, now within there imagine you can have very complex networks. A particular kind of network is called okay. So, when we have a single commodity network, it is like items of the same kind are moving through, let us say cars, okay, all cars. Think about a more general network where commodities of very many different kinds are moving through. Some of them might have different source and sink combination. The examples we studied were same source, same sink. It does not have to be. On a normal road network where you are starting and you are ending and I am starting, and it does not have to be the same, but we are sharing the same network. So, some of the paths we can sort of take up, share some common links. This is how your presence affects me and my presence affects you if we are both at the same time. So, depending on the commodities, you can have cost functions that are dependent on those commodities, like different commodities. It is like water and oil and some other heavier things flowing through the same network, like some things move slower than the other and they kind of obstruct each other's path and so on. So, those kinds of more general games, the behavior, like what is a deviating, improving strategy becomes lot more complicated and so on. So, that is the sort of generalized congestion games we are talking about. Okay. There that price of anarchy and all it's studied, but the values may be different. There are nice properties that an equilibrium always exists. In non-atomic selfish network, all equilibriums have the exact same value. Okay. All equilibrium paths have exact same value. That does not necessarily hold for non-atomic games and so on and so forth. So, those sorts of variations and so this is the thing, and all those studies happen via potential games. I mean all those sorts of analysis seem to all via potential games.
So, while Rosenthal was proving this, did he like suggest a way to get the potential also, or he just proved that there exists a potential? And
okay. So, when Rosenthal did it, no, there wasn't. You kind of have to come up with a potential function that captures that deviating behavior. Now, all these decades later, a huge part of game theory research and sort of aligned fields, sometimes a result seems so shocking, surprising, and people have been waiting for a result like this. It is oftentimes via a potential function that seems to come out of nowhere, like it is like almost like a magic. Okay, so that thing how to that is not clear. I mean that Rosenthal did not give it. So, anytime there are many games where the proof that there exists a pure strategy Nash equilibrium or an equilibrium of a certain special kind goes via exhibiting a potential function which has those desirable properties, and sort of showing this association correspondence between this space of equilibrium and the solution and how the potential function behaves and so on and so forth. So, long story short, no, there is no recipe. That is the part of the creative sort of research, this thing. Yes? Any other question?
Okay, good work. Yes, thanks, Sushmita, for
Thank you.